Hello everyone, my name is Anton and I'm like engineer from Chain Security, as I already was told. Who we are like in security of securing the smart contracts in 2017. This is a list of our awesome clients. I'm gonna like rush a bit in the beginning just because it's a lot of material to go through. And yeah, here today we want to give you like kind of our view on smart contracts, and that helps us to reason about really complex systems. And to start like going beyond the basics, let's go first into most basic reentrancy example. I mean, this is something you will find if you look on internet for reentrancy, right? And people, most I hope already know that here, for example, withdrawal function is vulnerable. Why it's vulnerable? Because if you have like high-level specifications that we want our balances, some of our balances to be balance, either balance of the smart contract by calling withdrawal function inside this call to message sender. Like message sender can be potentially a contract with a fallback function, right? You can potentially violate this specification, right? Like by looking at kind of patterns in this code, you can see that like we're reading some variables, we are having external call, right? This is a call to untrusted party, so to say. Like this is address that can be controlled by not the developers of the smart contract, but it's sort of controlled by message sender in this case, right? And afterwards we have write. Quite standard method how people dealing with fixing this problem is this check effect interaction pattern, right? This is already fixed code. You see the last thing here withdraw function does is call. So it's basically performs the same thing, but it behaves correctly with respect to like this external calls that might occur, right? So it's like pattern-wise regarding like read-write operations, we basically have call as a last item on our execution list, and as a result, anything message sender will do in their fallback function, it shouldn't affect our code, right? So this is where basics, but like what we would here, I will try to kind of introduce you is mindset how you can think about contracts as concurrent objects, right? Concurrency is like quite well-established field, right? Nobody has like a single processor on their PC now, right? Everybody has multiple, and there is like great effort done on like concurrency scientific field to make sure that operations are like behaving correctly when they need to, right? And the good way to think about this, this is still broken example, you see call in the middle. It's a good way to think about code in this case is that there is some execution thread, right? There is some thread that needs to do a work, in this case call withdraw function, and the external call to somebody who didn't write the code, not non-developer controlled code, is basically like a yield operation, right? In regular concurrency systems, like usually any operation can be yielded to some other thread, right? And you need to be sure that you are like establishing mutexes, which is like exclusive execution context where only one thread can operate at a time. Technically, it's super the same thing as like you have reentrancy guards, right? When you basically forbid any other contract, any other execution thread entering your contract again, right? By using these modifiers, right? Like to find the bugs using this concurrent smart contract as a concurrent object mindset, we need to think about what can be done during our yield operation, right? If we yield, there is a potential thread 1, let's go message sender controlled thread that can be executing anything in our smart contract, right? And as you see, like I here have kind of read-write patterns for not only like withdrawal function, but for any other function in our smart contract, right? So there is a deposit function. By the way, I'm here dropping some values. There's only basically storage values. If I have time, we'll take a look at the special value that is balance of account, because this is really special variable. But for now, like, let's assume that we only care about the state of our balances mapping. And as you see, like, deposit, withdraw, balances, all these three functions, they are kind of actually reading or writing writing to the same balances mapping as our thread 0, right? And like, why, what we can kind of get from this concurrency field is going to be next slide, packed with kind of my, I guess, interpretation of this theoretical works done before. I'm going to have kind of list of references in the very end of my presentation. But so in most cases, we can, from our experience as auditors, we looked at a lot of clients' code. We can say that worst case scenarios for reentrancies happening when developers are not assuming that their code can be executed in parallel, so to say, if their code can be executed with reentrancy. Because in most cases, developers are thinking about, so to say, sequential way of things. They're not thinking about like a call that can reenter, and this usually leads to the worst kind of bugs. Of course, there are some like protocols we had a look at, and developers who plan their smart contract around reentrancy, right? For example, if you have a router, Uniswap router that like it should reenter, or like flash loan smart contracts, right? There is a built-in function that calls the kind of hook to send funds for this flash loan, and this basically contract is intended to be reentrant, right? It expects to yield execution to third party, but there is like post-execution threads, post-execution checks that prevent basically this thread 1 from doing something that you don't want to happen on to your protocol, right? Okay, so the next point is that if we want like to detect that our smart contract is, oh yeah, sorry, it will be third point. But the second point is that if our concurrent object, which is smart contract, is linearizable, this is like a special concurrency property of this of this objects, is that the concurrent execution is equivalent to a legal sequential execution with respect to some sequential specification, right? So what does it mean? It means like if developers are thinking only in a sequential way, they only have like sequential specification, right? If their contracts comply with this linearization property, then most likely their code is executions, like reentrancy safe, right? And thus, to avoid unexpected bugs, we need to have our smart contracts like linearizable. Of course, assuming developers writing their code, assuming only sequential specification, right? And there is a really nice check from the kind of concurrency domain that if it's not linearizable, then you need to find two operations belonging to different threads, so to say, that are performed on the shared variables concurrently, and at least one of those operations is right. What it means, let's get back to our example. I kind of summarized, if you see on top like this conflicting operations, what this really means, right? So there is two operations that will be conflicting if they belong to different threads, they operate on the same data item, and at least one of those operations is the right operation, right? So by looking at this picture, we have pre-yield operations, right? And technically pre-yield operations already happened. We cannot affect them in most cases. Thread 1 cannot affect them. We'll see later like examples where it's actually important to also consider pre-yield. But in most cases, what we need to be sure is that post-yield, as operations that thread 0 gonna perform, not gonna collide with anything thread 1 can perform. And if you like follow these rules, you can see that our post-use operations are basically conflicting with deposit, with withdraw, and balances. And yeah, worst case scenario we know is like you calling withdraw again, right? This basically means that there is inconsistent, conflicting write operations on withdraw. But let's like think for a moment also. I don't know if people did this mental effort before, just to think about what reentrancy can actually mean for even such functions as like getter balances, right? If you see here, the balances is a public mapping, right? And you are reading potentially a field that's going to be immediately overridden before, overridden after the execution, right? So you technically, thread 1 will be already sort of reading stale data, right? While stale, because in post-yield execution of thread 0, it's going to be overridden, right? So, and the same for actually like a deposit. In deposit, its attack kind of doesn't make economic reason for message sender, but if you call deposit during the thread 1 execution, you're basically donating money to the smart contract. But nevertheless, you will break this invariant we have in the very bottom. The sum of balances should equal to this balance, assuming there is no, of course, this forced ether into a smart contract, right? This basically means that all these conflicts that our like heuristics from concurrency, this heuristic helped us to basically find all kind of things that potentially can break our balances, right? Our invariant, sorry. So I want to now really pay attention to that. We had the properties that the sum of balances equals balance of the smart contracts that we wrote our contract. With respect to this property, we wrote our smart contract and it got broken, right? But developers can potentially like write a smart contract that completely has completely different kind of specification, right? So in this case, for example, I wrote a smart contract, and it's kind of just snapshots the message sender, right? You see, like in the beginning, we are like reading old one, we're just calling him to notify for some reason, and in the very end, we are writing. We are writing the message sender, right? And developer can have like invariant in mind that basically last caller should be message sender, right? After my execution of write. And if you see how this function works, it actually has a correct execution. No matter what the old caller will be doing in his callback, he cannot affect the kind of assignment of the last caller, right? And if you look on the right side, this is basically the broken example of the isVault, right? This is classical reentrancy, and it has the same exact order of operations. And it's just the fact that we had different invariant helped us to sort of say that the contract on the left is safe and contract on the right is broken, right? So like going back to this really packed with data points, first of all, there should be a sequential specification without reentrancy, and only then, by using this method, you can reason if you have something unexpected happening or not, right? Because if developer had in mind specification like on the left side, it's actually reentrancy is safe, so to say. The reentrancy can happen, but it won't be breaking and violating the invariance of the smart contract, right? Yeah, I also have an example similar, where basically on the right side you have already fixed code, right? This is checked effects interactions pattern, right? And on the left side, this is last caller, but we're doing call as the last execution, like, and as a result, you can violate this invariant depending how you define the end of function call, right? assuming this function call ends with the end of the call frame, so to say. The old caller can call again the right function and snapshot himself again, right, and not the new caller, right? So it's, again, reentrancy is really hard problem just because there is this check effect interaction pattern, like you see here. It won't even be helping you because if you have specification in mind that doesn't comply with it, it's not going to work. So summary, the reentrancy vulnerability cannot be detected accurately without knowledge of smart contract specification. Yeah, read-only reentrancy-wise, yeah, we had suicide, but heuristic there is that you can basically check what you are accessing in pre-post, pre-yield and post-yield of your execution, and if there exists any way to combine your pre-post data that you have modified, then there's potential way to basically have a read-only reentrancy. I think Certora are going to present like a way nicer method. For this, their method, they're going to have like, I think, kind of symbolic execution and building a model, but I think it's quite good. Yeah, I guess I'm out of time, so I'm out of time, right? Okay.
Cool.